The word correlation can refer generally to any relationship between variables, but this section is specifically about linear correlation between quantitative variables. For example, these inputs define lists of values x and y, where y is constructed as a linear function of x, so x and y are linearly correlated lists of numbers. The relationship between x and y can be seen in a scatter plot using the elements of the lists as the coordinates of the points in the plot. This input uses the transpose function to turn that pair of lists into a list of pairs, and this plots that list of pairs as points in a scatter plot. The linear relationship gives a plot where all of the points fall on a straight line. Realistic data typically does not fall on a straight line like this. Here's a plot of data that does trend along a straight line, but the points do not all fall exactly on the line. If the points in the plot fall generally on a line that slopes upward, the variables are said to be positively correlated. If the line slopes generally downward, the variables are negatively correlated, and if the points are scattered with no trends up or down, the variables are uncorrelated. This correlation relationship is commonly quantified using a number called the correlation coefficient, which is defined by this formula. This gives the correlation coefficient for lists x and y. The correlation coefficient is traditionally denoted by the letter r. The correlation coefficient can be computed using the correlation function. For example, these inputs use the correlation function to compute the correlation coefficient for lists x and y. The result is a number between -1 and 1, where 1 indicates perfect positive correlation and -1 indicates perfect negative correlation. In some applications, a general guideline is that correlation above 0.5 or below -0.5 is considered strong or very strong correlation, and correlation between -0.5 and 0.5 is considered a weak correlation or no correlation, but those guidelines can vary widely in different applications. The correlation coefficient is unaffected by the scale or location of the data. For example, using the lists x and y from the previous example, multiplying by a constant or adding a constant to x or y does not change the correlation coefficient, and the correlation coefficient does not have units and is unaffected by units in the data. This input, for example, which uses data with units of centimeters but with the same magnitudes as in the lists x and y, gives the same dimensionless result for the correlation coefficient. It can be important to keep in mind that the correlation coefficient only measures linear correlation. For example, a scatter plot of the points represented by this pair of lists shows a prominent relationship between the lists, but that relationship is not a straight line and the correlation coefficient is a small number. The correlation coefficient does not measure correlation that is not linear. The correlation coefficient also is not a robust statistic, meaning that it is relatively strongly affected by outliers. For example, this plot shows points that fall mostly on a straight line, but where the correlation can still be small if just one of the points is far away from that line. In addition to the correlation coefficient, two other closely related statistics that are often reported are the square of the correlation coefficient, also often referred to as the coefficient of determination, or sometimes just as r squared, and a statistic called adjusted r squared. For example, this shows the linear model fit function used to fit a line to some sample data and returning the r squared and adjusted r squared statistics. The r squared statistic is the square of the correlation coefficient for the same data and is typically reported to provide a general indication of how well the data fits a straight line. The adjusted r squared statistic is given by this formula, where n is the number of data points and k is the number of non-constant functions in a linear combination of functions used to fit the line. When fitting a straight line to the data, k is equal to 1 and the adjustment is usually small. Adjusted r squared is primarily of interest when fitting a linear combination of several functions to the data, where it measures the extent of correlation beyond what would be expected for random data. Here's a plot of the data and the best fit line computed by the linear model fit function. The general topic of fitting data to a line is explored in more detail in the next section.